Thank you, Ian, for coming and giving us this. I'm sure it will be a very nice talk.
You know,
Yeah.
thank you to the Ian Mertz annual lecture.
Yeah.
Every time I have a layover in Lisbon on the way home from Christmas. It's always wonderful to be here. Always glad to see everyone. Thank you for Bruno for inviting me. And of course, I'll never pass up an opportunity to talk about the one greatest field in computer science, which is catalytic computing. For anyone who happens to watch this lecture after the fact, just be aware, I'm going to be moving a little bit slowly. Sorry about that. Such is okay, so we have this being recorded, so for posterity's sake, as well as anything else, we should talk about what catalytic computing is. It's more of a household name than it was last year, which was more than the year before. Every year we get new converts and whatnot. But nevertheless, let's talk about it. So we are dealing with the Turing machine model today. Hopefully everyone has seen this one since grade school. You have an input tape, let's say n bits, where the input to your problem is presented. This is a read-only tape. You can read as many times as you want, but you can't use it to write stuff down. The output tape is the converse of this. The output tape is going to be where you write down your answer. And oftentimes we deal with decision problems where you can just think of it as one bit, you don't have to put any restrictions on it. Today, we're going to be dipping into functional problems, research problems, and here we may have a lot of bits of output. So I'm going to restrict you. This is going to be write only, meaning you can't actually look at what you've written down so far. And for convenience sake, let's also say it's write once. So the tape head is pointing at the start. You write a bit there and it just automatically moves along. You don't have any notion where the tape head is. You have to keep track of that yourself, etc. Just making life clearer because we're working with space-time computation today. In the non-space-time world, none of this really matters for all intents and purposes. Today, I'm only going to give you S bits of free working memory. For some value of S, we call this class space S, and this class is the class of all problems that we can solve using just these three tapes. Typical instantiation of this, S is order log n. This gives us the class of log space, where we can do, say, undirected connectivity in graphs and such. Other typical examples would be polynomial in n, or even linear in n is an interesting one. What can you solve the linear vector space? This is in contrast to time. Time is perhaps the most typical thing that we optimize for. And you can even do time space. You can restrict yourselves on both of them at once. We're going to stick mostly to space today, but I will have some comments about time. Who's looking at this? And what's this in parentheses over here? Well, when we talk about models, Turing machine models, we can talk about giving them access to additional resources. So, for example, randomness, non-determinism, etc. And in the space-bounded world, this is no different. We can think of the class, say, non-deterministic log space, where I give you S is order log n, and I give you this full tape, which is filled in with some data. And the restriction is that yes instances, there should be some setting of the tape that lets you solve the problem. No instances, there's no setting of this tape that lets you solve the problem. Once again, I need to be very careful about how to use this tape. This tape, which is say C that's long, and again, for most of examples, C is like exponential in S. If I give you log free space, I'll allow you polynomial amount of random response terms, etc. But again, typically, for most resources you would want to study, most classical resources, this is a read-only resource, the same as the input tape, right? You can't be just erasing the randomness or non-determinism and writing down whatever you want. This would, of course, give you plenty of extra power. There's an additional restriction for most of these, which I think is not typically, like people who don't study space may not know, but it's very important that those resources are read once. So if I give you a non-deterministic log space machine, for example, I do not allow you to reread your non-deterministic bits. If you want to know why this is important, I claim that if you can reread your non-determinism, NL equals NP. You can just think about it for a couple of minutes. It's very easy to solve SAT as long as you can keep rereading the witness. Whereas if you can't do that, then suddenly it becomes much more difficult. So for space-bounded computation, this is an essential restriction. However, luckily today we're working with a different kind of resource, one which allows you to do anything you want with this tape. And this is called Catalytic. A catalytic tape is one where you have C bits, and as with all of these other resources, it's completely filled in. But I'm going to let you read and write to it, and I'll let you move around it freely as you see fit. And if I gave you no other restrictions, of course, we just start by erasing the whole thing and then using it as C extras in memory. So there's an actual restriction, but a scary one. The restriction is whatever this starts out in, and you have no control over this, you had better reset it to what it was at the end of the computation. So if I give you the all zeros tape here, I just give you a string of C zeros, then you're in a good shape, right? You do all your computations, huge amount of space, and then you just erase it afterwards. But this has to work regardless of what is in here. For any starting tape that I give you of C bits, you'd better reset to it if that's what you started with. That's the restriction. We call this thing C space S comma C. Again, typical setting of parameters. We said S is like order log n. C is poly n. And in this case, we have the class which we call Catalytic Logspace. A few housekeeping notes. You can make, we have this generic parameterization. You can actually mess with it. You can make C a lot smaller. You don't typically want to make C bigger than exponential in S because your Turing machine model gets weird, and one of two things is going to happen. Either your free space can't even address into this catalytic tape, at which point, you basically can just cut it off at 2 to the S bits, and that's generic. Or, if you can read the tape pad on this thing, then you can sort of manipulate that and use it as extra memory to get long C bits of memory. Basically, no matter how you define it, you're going to, the relationship between S and C is going to be at most exponential. But again, it does get interesting when you study specific things, like if you put in log squared n here, for example, we still know how to do some interesting stuff. So this is a pretty robust model. The obvious question about this model is, okay, can this do anything? Like, what could you possibly do using this additional tape if I just always have to reset it? Right? All zeros is fine, but if I can be incompressible stuff, blah, 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 it seems completely inobvious that CL should be any more powerful than that. Luckily, when this was defined by, I keep thinking, I want to say the B is for Bruno, but no, you come later in the acronym. So this is Harry Berman, Richard Cleve, Bruno, Michal Kotsky, Bruno Loft, Lawrence Spielman. They defined this model, and they showed, well, what's obvious? What obvious is that, say, CL is at least as powerful as log space because you have an L machine in it, and is most as powerful as P space because P space is when you don't have any restrictions on the metadata. They showed you can tighten this up from both sides. First of all, Catalytic Logspace is in randomized polynomial term. If I give you a polytime machine with access to coin flips, you can simulate any CL machine. In fact, you'll never even get the wrong answer. 2/3 of the time you get the right answer, the other third of the time you've got nothing interesting, and you can say, I give them. This is a very restricted form of randomized polynomial time. In fact, it's in like NP. And under commonly held beliefs, this is way, way within P space, which makes sense. The other side, however, is very interesting. They showed that a generic class called TC1 is in CL. And If you don't want to care about TC1, let's just say it gives you non-deterministic log space, randomized log space, problems like the determinant, and even more stuff. This is, again, under widely held beliefs, way outside of the log space. And this is pretty amazing. This catalytic tape seems to be more powerful of a resource than anything else we know how to give log space. Which is quite surprising because, just to reiterate, you have no control over what tab you get here. For NL, this is like advice from God. For BPL, this is purely random string. And yet, somehow, all of this fails in comparison. So this is catalytic computing. This was defined in 2014. There were some alternative models and whatnot. A structural theory of catalytic defined over the next few years. Randomized catalytic computing, non-deterministic, etc. Things went pretty quiet, and then in the last year and a half, 2 years, let's say, there's just been a complete explosion of work in this field. We had something like 19 or 20 papers over those 2 years, where there were 18 for the entire decade before that. So like things have been very much picking up steam. And in particular, the techniques from this catalytic role were used in this amazing result of Ryan Williams from last year, which I just have to mention. Which is that every computation, which takes time taken, can be simulated with space just square root t with a log t factor. This was just a totally shocking result, I think, to all of us. This says that, well, again, it uses catalytic techniques, but there's nothing about catalytic here. What's the trick? The trick is that once you learn how to use memory and reset it afterwards, there's nothing stopping you from basically just using the same memory over and over and over again. To do what you think of as requiring a lot of memory, just like continuously whittling it down by reusing these over. We don't know how far this technique can go. We don't know what it can be used for, but this is a pretty good sign that we're on the right track with it.
So when you say reusing memory, that's a bit, reusing kind of implies that you've used it and now you're using it again.
Yeah, okay. If I could go back to like 3 years ago and fix some of the nomenclature about this, which I defined, so this is my fault. I would, but nevertheless. Yes, so a hallmark of space versus time, kind of one of the things that people talk about as being the difference, is that once a block of time is gone, once a time step is gone, you're never getting it back, right? Time moves in one direction. As far as we know. Space, once you're done with it, good practice says just erase it and reuse it. In fact, good practice says never use memory to store what you can just recompute later, if what you're trying to shoot for is slow space bounds. This says something even crazier, which is that you don't even have to erase anything. You can take memory that's completely full, and think of this as like a hard drive storing whatever pirated movies you got or whatnot. And you can use all of that to do whatever computation you want and still end up back with it at the end. It's totally nuts. So yes, we call that reusing space. It's like maybe reuse plus. I don't know what you want to say. But yeah.
It's like using space while it's still being used.
Right,
But
using it for 2 things at once, or many things at once.
Yeah.
In particular, yeah, I guess space, you could think of as performing 2 roles typically. It's either being used to compute something right now, or it's being used to store something for later. These are like the 2 typical roles we think of as space in computation. This says, in some circumstances, you can use the same space for both of those tasks simultaneously. And again, with this repetition process, it also says that you can remember many different things in the same piece of memory. Which seems counterintuitive in terms of information theoretic standpoints, but again, recomputation is what really breaks the logjam on this. You've never, you can say you've lost memory at some point in computation, but as long as you can recompute it, nothing is ever truly lost. So the whole question is how much memory does it take to recompute, blah, blah, blah. And this takes it to its limit. So in a nutshell, this is CL. This list of problems that are in CL surprisingly hasn't been improved since this first work. We've been showing a lot more structural results about catalytic logspace, but the actual question of what you can compute in this model was never really improved. until the present work, where we showed that for the first time, there's a new problem we can throw on the pile, and this is bipartite matching, maximum chain. So let's talk about bipartite maximum matching. And this is where I immediately get in and out of my deck, because this is what I care about, and this is what my co-op cares about, which I should have stated right up front, by the way. So this is. This is a paper that we presented at Fox, I can say he presented at Fox just about a month ago. This is Ariane Agarwala, who's over at NPI in Saarbrücken. Great guy. If you get a chance to invite him to speak, he's really fun to work with and whatnot. I can plug him. In particular, I brought him in this problem when I came to visit the talk last year, because I was just talking about everything going on in Catalytic. He mentioned that he likes matching. I suggested some potential angle for proving this. He went back a month later, emailed me and said that he had it done. So, we took 2 weeks to write the paper for Fox, and the rest is history. Not bad for the first paper, I believe. Anyways, so let's talk about matching.
For what was known to be reducible to bipartite matching?
Good. Things that are reducible to bipartite matching, which are immediately implied by our results, include max flow when you have polynomial weights, i.e. weights which only have a logarithmic number of bits on the edges. Similarly for weighted matching, so maximum matching but with minimum weights, if your weights are only polynomial, that's implied by this. And min cut, still a max flow, that one actually works for all weights, even exponential size weights, because of previously known reduction. Interestingly, yeah, I did not know this, but max flow and min cut are dual. However, algorithmically, you know how to do more in the min cut role. So, interesting. Yeah, those are all immediately implied by our results. I'll say another thing which was not immediately implied, which took more work. This is by Ariane again, along with a couple of. There it goes. Oh, this is number 26, because this is coming out of ITCS in a couple of weeks. Linear matrix intersection is also in CM. Linear matrix intersection is a problem that's just a stone throws away from bipartite matching. It seems to be usually the next step that you go, apparently. In particular, it's got some nice mathematical structure which plays well with CL, but there was a significant amount of extra work that had to go into this. So they did that, and again, it'll be in ITCS soon. Stuff that we didn't get, all the problems I just listed with exponential weights, right? Polynomial length weights, polynomial big complexity weights. So weighted matching or max flow or whatever, as well as general matching in non-bipartite terms. This eludes us as well. I'm going to tell you, of course, this is Bruno's seminar. We're going to go through all the gory details and everything going on here, and I'll try and point out basically where the formula, where the framework fails to extend to these other things. It should hopefully be pretty straightforward, because essentially the high-level intuition about how you prove any of these results is the same, but there's the main technical hurdle is just an algorithmic one which relates to the specific problem at hand. So hopefully I can think of more of that. Matching. Anyone not seen matching before? Just wait. Yeah, so I'll just restate it. Yeah, you got a graph. In this case, bipartite, you have a bunch of edges crossing from left to right. You want to find out if there's a way of pairing up the vertices on the left and right, such that each of them shares an edge and you have no overlaps. Does this have a match? You can probably get this one by random chance.
No, please no.
Yes.
Yeah.
All right. What is it?
Oh,
Six. Oh, no, I missed.
No, there is.
I missed the vertex.
So there's an S from which you have to take two of them. And then you
Yes,
have
what?
like an S shape on top.
Yeah.
So you have to take those two edges to get it on some.
Yeah.
And
Yeah, that's right. You gotta take this edge and this edge. In particular, you have to take this edge because there's no other neighbors,
Oh,
which means you have to take this edge because this one's now offline. This one actually only has one other neighbor, left this one as well. And now we just have two vertices left and then you share, yeah, you just go across and across. Cool. Despite this is a hard problem. No, I thought that, but it's a problem that's existed since the early days of the field, and it's been a kind of touchstone problem for looking at with regards to both algorithms and complexity. So upper bounds, it's been known for a very long time that let's see, Hopcroft and Carter. This is polynomial time. We're going to go over, actually, there's like two main classes of algorithms for matching, and we're going to go over both of them because both of them are going to find their way into our result. So I should first say that I've studied with regards to polynomial time because this is, of course, the main thing that was studied back then, and it's a beautiful algorithm which finds its way into many other applications. A more interesting to me line of work,
Yeah, but this one is serious.
Serial. Yes, yeah, we're gonna talk about the advantages and disadvantages to adapting either of these to our purposes. Again, actually, we're gonna find things to utilize from both of them. So what Molay, Vazirani, and Vazirani showed in
There's also
87.
another paper by Vickerson and Ultron. That shows that matching is in NC2.
Mhm.
There's another paper.
It's either-
Randomization.
Yeah, I might be skirting over the body of related results on this. Again, I should just disclaim right now that I have any deep knowledge of the history of matching because it is an extensive one, a very extensive one. But let me just say for this one, they showed that with randomness, you can actually greatly reduce from polynomial time. Particularly, you can do it in NC2. If you don't really want to think about that, think about it as randomness plus like log space to the percent.
So there's this constructing a perfect matching is in random NC by Karp, Upfall, and Wigderson.
A perfect matching. Oh, I guess that this was extended to maximum matching.
No, these were independent papers.
Oh, really?
Yeah, these are.
Oh, they get
independent.
all the credit. Huh.
So this is 85. No, they don't. I mean, these papers are sometimes.
Okay, so then, sorry, who was it again?
The Karp, Upfall, and Wigderson, 85.
Okay.
You know, also maximum matching.
Does it do isolation though?
No, it's a different proof.
Interesting.
Yeah, it's a different proof. So
You learn something new every day.
but it doesn't have to be bipartite either.
Nice. I mean, this result was also extended later to, we have isolation based techniques that work for general graphs, I believe, right?
Maybe, so why doesn't yours?
Look at it. No.
What is RNC to how do you use the randomness in a circuit?
Yeah, no. So yeah, I'm actually gonna leave it as RNC. So what is RNC? So you have. Okay, everyone here has seen circuits before. Yes, been in circuits, right? So I'm just gonna shortcut around it and just draw it as this thing. Essential parameters. The height is like log squared n, or the log squared n. That's where the 2 is here. The size is polynomial. And at the bottom, you have inputs as well as random bits. So you have access to also the same random bits, right? So you think of your random tape over there as being labeled R1 up to RC. You can just use those as inputs. So down here is a mix of X1 up to Xn and R1 up to RC.
And this doesn't make a
It's the
difference.
same circuit,
So this
it's a
doesn't-
circuit of the same size and depth.
Oh, sorry, I'm talking about uniform circuits, just to be clear. So these are circuits, these are circuits for which there's a small Turing machine.
Same size and depth as what?
As then C2.
Yeah. So uniformity, sorry, I should stress.
But now you have random bits. And in the non-uniform model, you can always get rid of the randomness. Just by doing repetitions.
Yeah.
So, but here the circuit has to be uniform. And if you force the circuit to be uniform, then there's no obvious way of how to get rid of the randomness.
Yeah, the output here, for all choices of x1 to xn, i.e. your graph, you get the answer right with probability 2/5 over R. And as is being discussed, if we have allowed non-uniformity, i.e. we can sort of like pick the magic of circuit, we just pick a random string which does work for every, we can do error boosting, pick a random string that works for every input, and then everything is good there. You just need one threshold gate at the top, and that can be done in like long depth. However, we're talking in the uniform world where you need to be able to describe this circuit using like a, very fast, very efficient Turing machine or some other such thing.
Right.
Yes.
But this is actually like R det or something also.
Yeah. So the MPV result essentially says that if I give you access to randomness and to the determinant, then you can do it. Now, again, to be careful here, the rest of your algorithm, as long as you have access to the determinant, can be like logspace. That's fine. Except that you do need to reread your randomness. And so we can't just say it's in like BPL to the det or something. That read once condition that we said earlier also stymies in this case. If it didn't, if read once randomness was not, there would actually be very easy proofs of a lot of what I want to talk about today. That's not accessible. I should say to this whole point about uniformity, amazing breakthrough from 2016. This one, Fenner, yeah. I don't know all the people's names. Fenner, Berjar, and Tirolf. They showed that you can actually solve this in quasi-polynomial size than C2 without randomness. Now again, if I allow you non-uniformity, it's in NC2 by the above number. What they showed is you can actually de-randomize this algorithm with a quasi-polynomial size blow up. And it's not quite the pure de-randomization of this. This one ends up, well, as we're going to see shortly, this ends up generating a whole bunch of strings of length order log n, which are random strings of length order log n, which are useful. They round up and basically generate a whole bunch of strings of size order log squared n, which end up serving the same ultimate purpose. So it's a lossier algorithm than this one, but those log squared n strings are, I mean, they can just run over all settings of it over all the time, and it just works. Because it turns out that it's like there's one order log n squared length string that generates the whole line. So anyway, suffice to say, this is a problem where people poured a lot of attention into upper bounds for it, because two large glaring omissions, which I know from the beginning, are to get it in NC2 or the NC hierarchy without quasi-polynomial size or randomness, and to solve this simultaneously in low time and space. Mentioned earlier, time space is something people care a lot about. Is there an algorithm which works in polynomial time and what you call it, polylogarithmic space, the so-called SC classes? Big open problem. We really know, in fact, no algorithm that uses sublinear space and polynomial time, even if I give you access to additional resources. Unless you count catalytic space as an additional resource, in which case we get the very first algorithm, which works in logarithmic time, logarithmic space, polynomial time, and any additional resources. Because something that I didn't state here, this is in catalytic log space, but in fact is in polytime catalytic log space. Now, you know log space. You know that log space is in polynomial time. You know that there are only 2 to the s many settings of an s-bit work string. And if s is logarithmic, this means there's at most polynomial many. You know you can't repeat these. And that we're good to go. The question of whether CL is in polynomial time is been open since the very first paper, and we have no idea. Because we have to deal with the fact that there are 2 to the S times 2 to the C possible settings of the joint settings of the work tape and the catalytic tape. And so it is very possible for your algorithm to run in exponential time. It turns out that in this case, that is not the case. We know how to do this in polynomial time. And that is assisted, I mean, we can do it directly, or we can appeal to a previous result of ours, which fans of this seminar will have known this for the last time, which is that actually CL intersect polynomial time is equal to polynomial time, so CL. One direction is obvious. If I give you a polytime CL machine, it runs in polynomial time on every tape, including the all zeros tape, and it's in CL because it's just restriction CL, so it's done. Turns out the other way around is true as well. We're going to see it directly here. We're not going to appeal to this in a black box. It will end up being the same proof as this, just less generic. So, great. I should offhandedly mention that there's also a nice line of lower bounds coming out of matching, including some very beautiful recent work. So,
Could it be that there's some kind of general result that randomized CL, even with arbitrary access to randomness, is contained in CL? Is that something one might
it is quite possible.
believe?
Yeah, maybe I should write a little bit about how cool our model is for a second, since I didn't do it earlier, or I didn't do part 2 of it earlier. CL is equal to its non-deterministic variant, its randomized variant, and a whole bunch of other things. CL is one of the cases, in complexity we have a few cases where we can just kind of do it all. Now, space more generally, you know, if you have polynomial space, we know how to get rid of non-determinism or randomness using quadratic overheads. But we don't know it for log space. This is hugely open.
MACL?
What?
How about MACL?
MACL, yeah, all of them are in here. The constant levels of the hierarchy are in here. However, those need to be defined very carefully. Note for all of these, we're keeping the read once, read only restriction of all of our resources. Because again, otherwise things kind of seem to go haywire. And to Bruno's question, can we prove that we can do it even with read multiple accesses to all this stuff? I have no ideas for how that could be. I will say that. Again, if you were to do this in the log space world, you would show, say, NL with read multiple equals L. You're showing L equals NP.
Right, true.
And everything in between. Now, for catalytic, of course, is magical and do everything, but like, I don't know how to prove it.
No, but for randomness, there would be the chance that you don't get the same thing.
Sure, but then we wouldn't know that BPL is in P, for example. Read multiple randomness log space is not known to be in polynomial time. It's in BPP, that's all I want to know.
I see.
In fact, even like, I think as low as BPAC0, we don't know. Maybe BPAC0, we know it's in P. BPAC0 with parity gates, no. Yeah, there's this weird mismatch where BPL is the only class really defined as read once randomness, and so that's the only one we know how to put in P.
For PP with parity gates, can't we use?
You need PRGs or something like that.
Yeah, but don't we?
Yeah, I think, yeah, for whichever class we go, PRGs we're fine, and then outside of that, we've got.
Okay.
Again, BPL doesn't use, well, okay, BPL has a PRG, which can be hooked up in polynomial time. You know, this is not generator, so. But again, that only works against read once. You can extend it to work against read logarithmic number of rounds or something like that. By increasing the seed length appropriately, although I no longer know if it's in polynomial time. Anyway, the point is, one has to be careful about all those things. MACL and whatnot, all of this works fine, but you have to be very careful about how you define it. So MACL is like, you get non-determinism and then you get randomness. And typically it doesn't really matter, right? It's like, there exists this non-determinism such that for 2/3 of random strings, blah, blah, blah. In this world, not only is it read only, not only is it read once, but you have to finish reading your non-determinism before you read your randomness. Or if it's AMCL, it's the other way around, right? You have to finish reading your randomness before you read any of your non-determinism and you can't go back. This is key because otherwise, again, there's like easy algorithmic arguments for how you can get NP. Well, not easy, the PCP theorem. The BCP theorem works if you can just interleave your randomness and non-determinism even slightly. Right, because it's only a constant number of bits are needed. It's like when you give me the non-determinism, and then I use randomness to check 3 random places and something like that. I need to be able to pick those 3 random places, then read into the non-determinism. And the random non-determinism can't depend on the randomness. So like somehow to fulfill all these criteria at the same time, you need to be very, very strict about how you define it. Branching programs make this easy, right? You have a whole bunch of layers which are non-determinism, then you have a whole bunch of layers that are randomness. Luckily, we do not have to deal with any of this today because we're working with deterministic algorithms. But yes, if you want to wade into the weeds of all of this, we have a pretty short paper from last year which showed all of these results, and we sort of discussed where you need to be a bit careful, as well as potential for the future. Right. All right. Which year was the most problem result? Because 87. The lower bound against matching, the monotone circle.
Oh, I don't know.
So Rasmussen showed that this function is actually hard to compute with monotone circuits. It requires some positive polynomial size. Even though, again, by the whole discussion that we had earlier, this is a non-uniform monotone circuits. By contrast, here, if you wire your randomness or whatever, polynomial size, log squared depth is enough. So the non-monotone gates are non-monotone computation does not work. Different topic, roughness. So Roth has shown that this notion called the extending complexity of the polytope of matching is exponential. And this is again some notion of hardness that's related to monotone circuits and whatnot. And suggested what would eventually turn out to be true as of just a few months ago. That actually the monotone circuit size required for matching is 2 to the n of the 1/3 at least. This is actually very close to the best known monotone circuits lower bounds we have against anything. And this even applies to a weaker function than matching. If I recall. Just double check out. I think it applies to one.
That's a 5.
1/3. Yeah, everything is in I guess circuit size and 2 equal to 5. So, but at least one. But yeah, no, this is very nice piece of work by Bruno Cavalar, Mika Goose, Arthur Ryazanov, who is here, which was about Anastasia Somonova, who has visited here, Russian. And Dima Sokolov. Cool. So this is a problem that, again, we really care about proving lower bounds for it because we feel that in restricted models, this is actually a very hard function. So even though I guess ultimately it is widely believed this should be an NC without the R, although this is a point of contention, it's totally unclear for polytime, polylogarithmic space, etc. And in particular for a lot of the models that we care about, where we can prove any sort of lower bounds, we can actually get very good stuff against matching. So great problem both in algorithms and complexity. And again, it's got 2 different techniques. I guess into the third point here. It's got 2 techniques that I have. And we're going to leverage both of them today. So you're gonna learn two ways to solve matching. We're gonna put them together along with some catalytic magic to see the third generic coolest way. But, well, any questions about this side? Everyone happy with this? Great. Anyone need to take photos or anything of this? I'm gonna start over a second. Oh, yeah, right, of course. Whether I like it or not, I'm being preserved for posterity.
Yes.
I just should say, if you want to learn more about catalytic, there's a survey from 2016 by Michal, as well as a survey by myself in 2023. These will both give you decent introductions to the kinds of problems that we care about and the techniques involved. It will give you no information about the state of the art, because the whole state of the art has been defined in the last year and a half. So if you want to know what's happened, I guess I went on a speaking tour this year, and there's some recordings online. For some of them, I explained what's been going on. But the field moves very fast, and the techniques are very nice. In fact, we're going to see at least one of them today. One of the other one is hiding underneath the hood, but we can talk about it. I know River doesn't like things being hidden, but great. Oh yes, the point I was talking about earlier with regards to the read multiple randomness not being in P. It should be noted that matching in P and matching in RNC2 are technically incomparable results. RNC2 is not known to be, and obviously P is not known to be in RNC2. All right, this one I'm gonna do a little bit by picture. This is the augmenting paths algorithm. Who has not seen augmenting paths? I'm gonna go through it. Okay, cool, that's fine. So the idea with augmenting paths is the following. I want to construct the largest possible matching. And to do that, I'm going to start by constructing whatever matching I can. Let's say a matching of size 1, also known as an edge.
There's colors there, maybe it'll help.
Aha. Green, maybe not. All right. This is my matching size for that. Can I do any better? Yes, I can. Good. So of course I can observe the fact that I can just grab a different edge here and call it count. But there's something more interesting we can do, and this is called an augmenting path. An augmenting path is the following. It's a path in this graph, and of course because it's bipartite, that means it's going to go back and forth, where every edge, like after I take an edge that isn't in the matching, I have to take an edge that is in the matching, and alternate this way. So one way to enforce this is take the original graph, and we're going to add directions on all the edges. The way we're going to do that is every edge that's not in the matching, we're going to direct forward, and every edge that's in the matching, we're going to direct backwards. And now an augmenting path is just a maximum length path. What's the longest path we can have in this graph? Yeah, well, I mean, first of all, just by definition, the longest path is going to have at most like one one, like the last edge and the first edge are gonna be, going toward, like, this direction. Because after that, if I want to get back here, I have to follow a matching edge and so on and so on. I guess I could do it the other way over. Yeah, I guess I could do it the other way. Oh wait, no, sorry. An augmented path can be any path, like any path on this graph, but the ones that are actually going to augment this up to a new matching are ones that start and end on the left-hand side. In other words, it has to start with an edge that's on the matching and it has to end on an edge that's on the matching. So in this case, so if I want to use this thing, I have to take this edge, then take this edge, and then take this edge. Right? And now I can't go any further. So what's the idea? The idea is that our matching of size 2 is going to be exactly what happens when I just flip which edges are in the matching, which ones aren't on this graph. In other words, I'm going to delete this edge from the matching. But in exchange, I have to add the other two edges. The whole drill about this, of course, is that if I want to take either of these two edges, particularly if I want to take both of them, I'm going to have to erase this edge that I used before, right? The vertices are being taken out. But by taking this augmenting path, we ensure that these two vertices, which are originally matched, stay matched. Good. And now, of course, we can do it one more time. We want to find an augmenting path of length 3. Well, and so again, let's cross off these two edges, and I add these, and I get my matching. Now we're going to extend it because I have actually a perfect matching. I get matching of all the vertices. Now, it could turn out, by the way, that like we also have this vertex down to that either got matched at the beginning or at some point. This won't participate in any of the augmenting paths, right? I can't do anything with this edge. So all I want in order to accept matching is actually to find some augmenting path somewhere in the graph. It doesn't have to include all the edges of the matching. It doesn't have to have any restrictions like that. If I can find any augmenting path, then I can replace at least, whatever it is, m edges with m+1 edges in the matching. In particular, I can grow my matching by size. So, by the way, when this is done, essentially you would just look for another augmenting path, and the only one that exists is just this edge by itself. Right? This edge by itself is also an augmenting path because it starts outside of matching and ends outside of matching. That's all we do. And it's maximal, right? That's another restriction. Maximal means, in a sense, like the only restriction on maximal means that you don't have a backwards edge on either side of it. And that's all that essentially means. Good. And I forget who's doing this, but it turns out that to construct larger matchings, augmenting paths is necessary and sufficient. In other words, if I have any matching of size k, and it can make and there is a matching of size k+1, you can obtain it via augmenting paths. Which is surprising to me, but
Well, you cannot obtain it by augmenting path.
oh, sorry, you can obtain a matching of size k+1. If one exists,
Right.
then you can obtain. Thank you. Yes, if there exists a matching of size k+1, it can be if you have a matching of size k and there exists a matching of size k+1, then it can be attained via augmenting paths. Is that right?
Nope. And some
That's also
And some matching of size k+1 can
yeah.
also.
Yeah, if there's matching of size k,
If there's a matching in one of.
if there are any matchings of size k+1, you can
Actually,
obtain a matching.
Maybe write that in. So
Okay.
the theorem means the following, that suppose you have two matchings, M1 and M2. Right, M1 and M2. M1 and M2. Right, think of them as giving red and blue. So suppose that M2 has k+1 matchings and M1 has k.
This is in like, so this is size k, and then M2 is size k, right?
Now look at the.
This is actually different.
Yeah, something like that. So look at the graph that has the edges in M1 written in blue and the edges in M2 written in red.
Yes.
Right? And the claim is that in this graph, there is a,
There is an algorithm.
Yeah, so what would that mean? So,
Just take
No.
just take any red edge, which, yeah, good, right, so you have your red and blue edges.
yeah.
Yeah.
So that should mean that in the graph, there should be a path which starts and ends with a red edge.
Exactly, and the reason why
And
is
it's an
because,
augmenting path.
there's one more blue edge than red edges.
No, there's one more.
There's
There's
one more one color than the other. And so in particular, if you just start. How does this work? What happens if that was not the case? For every blue edge. There's either,
So, okay, let's just start, right? So you start with a vertex that is red matched, but not blue matched. It must exist because
Yes.
the red matching is big.
I did the colors backwards, sorry, blue match, but not.
So start with a vertex that's red matched, but not blue matched. So there's more red than blue. That's it.
Here there's more blue than red. Look at-
I wrote as well blue.
Oh, more blue than red. Okay.
So yes.
Okay, so start with a vertex that is blue matched, but not red matched. Now follow that edge.
Right,
Just follow it. That's gonna be I claim that can be the first edge in an augmenting path. So just follow it.
I actually don't, no, that's not true because I picked this vertex.
No, that's okay.
Okay.
Oh, I think,
No, here's what it is, so if you do this and you end up ending on a red edge, just follow past those. It either ends on a red edge or a blue edge.
Yes.
If it ends on a blue edge, then you have an augmenting path,
Yes.
right? If you start on a blue edge, you end on a blue edge. If you end on a red edge, you consume an equal number of blue and red edges. Now just apply the same argument to the rest of the graph. So you go here, you're just gonna ignore this part, go down.
It was still okay, yeah.
Right, it's still the case that there's more red, blue edges than red edges. So you can do this until eventually you just find one that ends there, and that's your augmenting path. Good, this gives you a matching necessity.
Francesca, is that cool?
Yes.
Yeah, we're all learning this together. It's funny because an argument like this is gonna appear later.
All right, so how about the RNC squared?
Right. So that should probably take out because you just, this requires whatever, like, essentially ST connectivity. Or something therein, something that you can check the polynomial time. For every pair of vertices, to check if there's an augmenting path between them or something like that. Using this graph, which we call the residual graph. The graph where you have the arrows forward when you're not and matching the arrows back when you are. So you just check our augmenting path between these two vertices, like spaghetti vertex over here and any vertex over here. If there is a path, it's an augmenting path. Good. Sorry, it has to be a maximum path as well. So you just have to check that there's no outgoing edges on either endpoint. And you can repeat this 10 times, and eventually you will hit the highest possible matching, and that will be it. Good. So that's a polynomial algorithm. Good things about it. Deterministic. Pretty straightforward, all things considered. Annoying thing about it, very sequential. So, in CL, we can hope to do all kinds of stuff related to this, right? I can do actually directed connectivity in CL. I told you before, NL is in CL. But great, I can run one iteration of this. Now, where do I write down what I have so far? If I have to store the matching that I have in order to run augmenting paths on it, I'm going to quickly run out of space to do so. I can only store a constant number of vertex names, for example. So I can only store a constant number of edges. In the matching. So to try and go up to matchings of size n, this is not going to do this. However, keep this notion of a residual graph in mind. It's going to be quite helpful. All right, RNC tape.
Suppose you could somehow do this in an invertible only. So I'm wondering, can you use the catalytic space? Kind of, probably not, but you do some kind of delta with what's there.
Yes, the problem is, well, first of all, storing what's there would have to be done in the catalytic table. And then this takes n rounds, right? So if at every round I have to recompute what happened in the round before me multiple times, then my recursion is like, even if I have to do it twice, it's like 2 to the times, or it's twice to get the n1, I have to compute the n minus first. Each of those I have to compute it twice to get the n minus second, and in the end, this is an exponential time algorithm. And even just figuring out how long I've been running will take me a polynomial amount of the spacing frequent. If I want to run for polynomial time in a catalytic log space machine, I have to actually do a lot of forgetting. I can't remember how long I've been running for. You have to halt for other reasons. So none of that's gonna work. As far as I know.
Right, cool.
Yeah. So we're actually, just to already give you a sneak peek. The good news about this is that if I can generate a size k matching, say via a CL algorithm, so anytime you need an edge, I can generate it for you. And I don't worry about this recursion or whatever. I actually just say, I know there's a size k matching, if I can generate it via this algorithm, then I can use augmentation to find a k plus 1. Now, that's not going to be, we're not going to just, again, repeat this process. It's going to turn out that we're going to do this in a sort of parallel format. And the way we can do parallelism is via the RNC2 algorithm. That's a pretty good segue. RNC2 goes via a totally different method. So RNC2 says the following. Imagine I'm going to actually stick weights on all the edges of it. So as is, there's no notion of a weight in this thing. Every edge is just an edge. And every matching is just the number of edges in the matching. However, I'm actually going to give weights to all of these edges. And why am I going to do that? Well, it turns out there's this third algorithm that I didn't tell you about, a way worse algorithm, just in terms of complexity, and it's the following. Matching reduces to the permanent of a matrix. Does everyone know what the permanent is?
Sorry,
The permanent. Do you know what the determinant of the matrix is?
the determinant of matrix.
Yeah. So the determinant of the matrix has this plus minus one. Like there's this equation for it, which is like that of with the sum over all I and one and either the rows or the columns. It doesn't matter. And then it's the it's the product over all the permutations, right?
Products from 1 to n.
The sum is overall permutation.
You can dive.
Good, thank you. Oh. I know the operational thing, but I don't remember the specific formula. Yeah, the sum of all permutations.
No.
Like the other way.
Yeah, you
It's the
cannot
sum in sigma of the products.
Wait.
It's an OR overall matching, so it's a sum.
It is an order column. You're very correct. So the sum of all permutations, is it?
Yeah, sum in sigma.
Yeah,
Permutation.
right. And now it's the product over all. Oh, I was trying to do the recursive one. So it's minus, right, there's a
Minus
-1 to the,
sigma.
yeah.
Sign of that.
So the to the sign of sigma.
Yeah.
Well, sigma times the product of all elements in the that's right? Okay, cool. Permanent is without this. That's it. Great. And as Bruno says, this is very nice because if I stick in the matrix, which is the original graph, I'm trying to run matching on, and I take this permanent form of it, it turns out that when you look at all these permutations, this exactly is just you have to select for every I on the left hand side, something that it goes to on the right hand side should be the sigma. In particular, in the matrix, it's just like for every I you pick a J, which is going to be mapped to. And since it's a permutation, you don't get to reuse anything, which is why it corresponds to exactly the matchings.
Right, so the permanent of the adjacency matrix is the number of perfect matches.
Correct. What is the entry here? Well, it's an adjacency matrix, which means it's either 0 or 1. If I select all of these to be 1, then it's 1. If any of them is 0, then it's 0. And as I just point, you get all of them to be 1 if you actually select a matching. Which means when you just sum up over all sigma, everything that's not a matching dies, everything that is a matching survives, and you just count the number of perfect. Perfect matching meaning you get all of the curves. Good. Problem is, can't compute perfect. Just very hard. The determinant is much easier, it has all these like expressions for it, simplifications, etc. But this -1 now causes a problem. Because if half of your matchings have odd sign and half of your matchings have even sign, which is some quantity that's out of your control, then you're just going to get 0. So we're going to introduce these weights to get around that. So the edges are no longer going to have weight 1. The edges are going to have weight 2 to the W of D. They're weighting on this. Now the reason we pick 2 to this, well, okay, it's going to become clear in a second why I need exponential in this. Why didn't I just these weights be large in the first place? Well, first of all, I can like this n is actually going to be like kind of funny that capsules that being used the other way. Oh no, sorry.
Oh, yeah.
Yeah, this is going to be 2 to be long. There we go. So it is going to be polynomial. Yeah. Yeah, but it's also going to actually be quite useful that we have these as being 2 to the weight of the match. In fact, this is where the matching is going to come from. So let's just do a sanity check. If I have a matching, if I don't have a matching here, I still get 0. Nothing changes. If I get a matching, what is its product going to be? It's going to be exactly 2 to the weighted, the sum of the weights of the edges of the match. In other words, 2 to the matching sums. And then we still have this problem. We can get cancellation. However, if we can just isolate one power of 2, which can't be canceled out by any of the others, then we're good to go. In particular, let's say all of these matchings have large weight, except for 1, which has slightly smaller weight. Then if you just look at these numbers as binary, the one with the smallest weight is going to have a 1 in some low order
So
position.
what you said is not exactly true.
Mhm.
Right? So what you said if we could isolate the matching with the particular weight would be done. That's actually not true.
No, smallest. Just sorry, with a lower order bit than the rest of them. If it has a bit that can't be canceled. That's true.
Right.
Right.
Yeah.
So if I isolate some mid-weight matching, it's possible that I can sum up a whole bunch of smaller matchings, so matching with smaller weight, all with the opposite polarity and cancel it out. However, if it's the lowest order bit on all of them, then you'll never cancel that out. Because no matter what happens with the rest of the matchings, adding, subtracting, etc., that bit in the binary expansion of the sum is going to be left unperturbed. And so we need to claim that there is some weighting assignment such that insofar as a perfect matching exists, the mid-weight perfect matching is unique. And it turns out that that is not just true, it's true with high probability. And this is the isolation. Now this one I can probably actually put. So,
Can you write it for any set system?
yep. Oh,
Because it's nice. It's very general.
probability over randomly. Yeah. Are using this to say there exists a unique set in the set system F of min weight. This is at least 1 minus m little n of the power. where little n is the size of the universe that I'm taking my set system over, and capital N is the size where I'm taking the weight function. So we take a random weight assignment, and this capital N is, some polynomially larger than little n. The probability that I get a unique min-weight set in the set system under this weight is very large. And a beautiful thing about this is this says nothing about f, including the size of it. You can take this side, the set f to be like all subsets, all non-empty subsets. Yeah, ignore the empty set. It still works. This was okay. Actually, a similar lemma, I guess, appeared in a previous work by Sipser and Wickerson, or no, Sipser and
You mean the card who forms Reapers?
no. It was about unique key. It was not about.
You mean UP? Like
Sure.
answer this is to UP?
Yeah.
Yes.
There was an isolation on the paper before it, but this is like MVV, the paper that I thought was the only relevant one here, is the one that kind of coined this and got an algorithm.
So sad, but if what was it? If UP is in D, then NP plus P.
Something like that.
And this is D.
But maybe Sipser Valiant, maybe. I should do this. Anyway, the point is, because this lemma exists, then we just pick a random weighting function. We're going to compute this determinant using these exponential weight functions. And as long as this holds, which holds with probability much less than greater than 2/3, we're good to go. This tells you that you can compute matching as long as you essentially have access to the determinant, the ability to do all these like small reductions, like exponentiating the weights and whatnot, and most important, randomness to come up with the weight scheme.
And where does determinant lie?
Determinant lies in this class called TC1, which is well within NC2. So our NC2 is a good order. L to the determinant C, well within NC2. So actually, you can write this down. You can probably say RTC1 or something like that. It'll be fine. Just no one cares about TC1. Point is randomized small circuits.
Value fuzzy then.
Oh, it's VV. Oh, Vassar. Okay. This one is by MVV. One of the V's overlaps with that one. It's actually, I don't remember.
Isn't it both? It's both.
Well, there's two V's. in this
No,
one.
I think they're both fuzzy then.
Yeah, exactly. I don't know which Vassar at least that. The brothers. The would not just the world's strangest coincidence. Great. Advantages to this algorithm. Works in parallel. All you need is the determinant. All you need to do is compute the determinant once. Well, I'm CL. I can do that. Determine Z. Problem. I need randomness. Randomness. Well, again, CL equals BPCL. But as we talked about before, this is read once randomness. You need to be computing this determinant, which means you need to be constantly rereading these weights, whatnot, in order to do the actual fast algorithms for determinant. Right? If you want to do row reductions and all this kind of crap, this, need to do this. Nevertheless, we're going to take elements from both of them.
Oh, are you gonna use the catalytic as your weight?
You know it. All right.
And then you compress it and not really compress.
Correct. Step one. Split the catalytic tape into two different chunks. One of them is just used for normal CL stuff. In particular, we're going to set this aside for the image chunk. Right? Some log free space, some catalytic space. I'm just telling you as a black box that you can compute the determinant in CL. Again, if you want the peek beneath the hood, we can go into some very interesting mathematics, but this is not what the paper is doing. This has been known since 2014. We need to make a slight adjustment to it, so that we need to be able to compute the determinant with large weights, polynomial bit weights. This is not technically implicit in the original paper.
It's not TC1?
Not obviously. But it's not the way that it's. Oh, maybe no. It doesn't matter here. It's easy. It's quite possible. Multiplications in log space. Yeah, maybe it's okay.
So there's this NC2 algorithm for computing the determinants, so recursive algorithm by some guy, I forget his name. It's probably a DC1.
Yeah, it might work. Might be okay. Anyway, I'm telling you that it works. So just see. We put a lemma about it on the paper just in case. Anyhow. The other section of catalytic tape is going to be our weight function. And why is this going to be useful to us? Well, this follows in a paradigm which I came here last time to talk about because it was hot off the presses. This is a technique called compress or blend. And this is one of the two big ideas in it. So when I said earlier that if your CL machine just gave you the all zeros catalytic tape, you could do whatever you wanted, but you might assume that it's incompressible or something like that. Turns out that that already has a grain of interesting truth in it, which is to say, a string generally is either compressible or it's random. Now, compressible is of course going to be the big challenge. You have to actually run a compression algorithm, but ultimately it's either random or it's not. And if it's random, then we have access to randomized algorithms. And if it's not, then we can hope to actually compress the thing using its lack of randomness, free up a bunch of memory on the catalytic tape, and eventually just run some brute force out of like a polytonic algorithm. That is going to be the big paradigm in which
You can always test if you had the perfect matching by doing that.
Correct. So right, let's start checking all the boxes. So this alone is enough to tell you that if you run the determinant using this as your weight function and it returns a non-zero answer, you have a perfect matching in the graph. Right? This is already enough to. The problem is when you have perfect matchings, but the weight function isn't good enough, and so you don't get the cancellations. Do I need to talk about the gadgets and whatnot? Let's talk about the gadgets real quick. So I've been talking about maximum matching, right? But everything I've said is about perfect matching. Turns out we know a lot of tricks to reduce between these two cases, and I'm going to talk about a few of them now. Because ultimately, we are going to be trying to go from k to k plus 1 at every step. But we're going to do it in a way where the recursion is well. So just to get some stuff out of the way, let's imagine I have my graph here. And I actually only want to test, not for a perfect matching, I want to test if there's a matching of size exactly 2. So, I've got 4 vertices, I want to check first, get that thing of exactly 2. And, there's stuff going on here, and control. The gadget is easy. I'm going to have to soak up 2 additional vertices on each side, right? If I want a matching of size 2, then I'm going to have 2 vertices on each side which are unmatched. Well, I'm just going to create somewhere for them to go. I'm going to create a complete graph, divergent graph between an extra 2 vertices here and all 4 vertices up here. And I'm going to do the same down here. Good. Now, it turns out that if you have a size k matching in the original one or a size 2 matching in the original one, you have a perfect matching in this. And vice versa. If you don't, you don't. Furthermore, we can actually deterministically pick some edge weights here, such that there's a minimum contributing to this. There's a minimum here. Now that sounds like surprising, but it's because these are complete graphs. So I can actually deterministically choose some edge weights here, such that, well, first of all, we're going to take, what's my ultimate weight function going to be? It's going to be like, take the weights up here. So the weight of an edge in the graph, in G, the weight's just going to be like 10 W to the fourth or something like that. I'm just going to make the weights, make the weights way bigger from the original one. So I have a whole bunch of area to work in on the lower bits. And the way I'm going to do it is just say E is not in G, W prime E is equal to like index of U times the index of V. where these, you just choose some arbitrary indexing on the sides.
So you still want there to be a minimum weight isolated.
Correct. So what's important here? What's important is that if there was an isolated one in the original graph,
Times n squared or n to the fourth instead of w to the fourth or something. Because w could be one, right? So probably mean that times n to the fourth.
oh, yeah, there we go. Yeah,
Okay.
good call. So the point is, if you have an isolating assignment in the original one, well, first of all, high order bits are still going to be isolated, right? So obviously any weighting from the original graph, which has a larger weight, is gonna be like way larger than this because I've just moved them to the larger bit. So even if somehow some choices down here got weird, it wouldn't change which is the minimum weight assignment. And then it's pretty quick to check that the exact correct edge choices down here are like, you pick the lowest index guy here and match it with the highest index guy here. Meaning like, there's some vertices that are left over by the unique midway matching. Pick the highest index one over here, match with the lowest index one over here, and just continue doing this.
No view.
Yeah, it's just some like, it turns out that like this will isolate the mid one, if there were two, it's just a contradiction. It's just the usual way, like X and Y was A, it's still separated, something like this.
Yeah.
Just analyze this thing and it works. So good. So that's a gadget for doing exactly matchings of exactly size K, and all of these reductions can be done easily. But you do a weight function, you compute this, you compute this, you do everything you need. Great. So is that the only gadget? Oh yeah, and then just another small comment. I said I want to output a maximum matching. If you get an isolated matching of some size, then it's easy to test. Of some maximum size, it's easy to test which edges are in that isolated matching. Like just basically toggle the edges in and out one at a time. So once I know that I have the right answer, like I have a maximum matching of this size, and I have a weight function that isolates it, I can just basically do a bunch of like hacking through it to figure out which edges are in the matching, even if I can't write them down one by one.
Right.
This is all just a little hackery. If you only care about the decision problem anyway, then like just take this.
But this is
Or the decision, not the decision problem, the problem that tells you which K is the maximum. So,
in the search problem.
This
You
you
mentioned.
just say there's a reduction.
yeah, this part's fine.
So you want to, I mean, when you're doing this thing of finding out which edges are in the matching, you're finding out which edges are in the minimum weighted matching.
The minimum weight matching, the mid weight maximum matching.
The min weight maximum
Then
matching.
perfect matching.
So that means-
Yeah, the mid weight perfect matching in that
Yeah.
gadget. So you
Right.
pick the K for which it works, and then you do this. This gadget will give you perfect matching, and now you can do some tricks to figure out which edges are perfect.
And here it's important that we're not changing the weights each time. So
No, correct. You're gonna fix some weight function which you know works. That's all. By the way, this algorithm is going to have a property which I very much do not like. And I want to fix it, and this is I think a really nice current line of work in Catalytic. For decision problems, it is irrelevant to say that for every setting of the catalytic tape, you get the same answer. Right? That's how deterministic algorithms work. You either get zero all the time or you get one. If you're just trying to output the size of the largest maximum matching, that's also true here. No matter which catalytic tape I get you, you will eventually get the right answer. If I ask you to output a maximum matching, then you will get the one that is minimum under W. And W is given to you on the catalytic tape, and you have no control over it. And this is a property I really don't like. This is like, I want a quote unquote pseudo-deterministic algorithm for CI. I want that no matter which catalytic tape you give me, or maybe with like overwhelmingly high probability, you always get the same matching. And this I don't know how to do. It's interesting because I can test whether or not an edge is in a maximum matching, and then I can try and do some like whatever Lex first tricks. But it's not at all clear how it's actually going to go all the way through when you're trying to output these edges one at a time. So great open problem, but we're jumping ahead of ourselves. Everything that we've said is assuming I have a random W. Then with overwhelmingly high probability, everything that I just said goes through, you can find out exactly the K for which this works. And why did I say exactly the K? Because you just can run this first with K equals 1. You know, you try and find a 1 matching, then you try and find 2 matching, 3 matching, 4 matching. Eventually you're going to see a 0, and assuming W is good, you're going to take it on faith that that is a good situation. And now what we have to deal with is the compressed part. What happens when I give you garbage productively?
So let me get the idea. So the idea is the probability that W being isolating is very high.
Yep.
So if W is not isolating, it must come from some small set,
Correct.
right? So I should be, so if I can find a way of efficiently encoding the weights that come from this smaller set, and I can do this compression in place, I just compress W actually.
Correct. And by the way, that for everything I've said here, there is no difference when you go to non-bipartite matching. Maybe the gadget gets a little bit weird, but I think it's fine.
It's the compression you know.
Correct. The compression is going to be very targeted towards this. In fact, I can actually tell you where the compression is happening, and that too is very generic. In fact, a 1995 proof of the isolation lemma, a reproof by Spencer, actually just tells you what my compression is going to be. It just doesn't tell me how to find it and how to decompress. Those are going to be the hangups, and those are going to be all the work you have to do to more generically apply this framework. Right now, everything I've said applies anywhere with the isolation lemma. As long as you can compute the function, assuming your thing is random, everything here works. The whole trick is to say, when the isolation lemma fails, can I find this, find what's responsible for the failure, compress it, and then later decompress. And let me say right now, if you can compress, by which I mean we're going to take some section of catalytic tape of however many bits and replace it with fewer number of bits, then you're going to iterate this process, right? You've saved some number of bits here, just take some more catalytic tape, just keep tacking on more catalytic tape. You know, we are allowed polynomial amount, you can just keep lengthening it out, you know, we can just assume it's however long you need it to be. You're going to compress until there is like, say, n squared free space or something like that. Let me just run this out. We have n squared bits of free memory, it's all zeros, just run a polynomial. And that tells you why this is in Catalytic Logspace in polynomial time. Because these algorithms that I've described are all polytime computations. And the compression will also be polytime. So either you have to compress, say, n times or n squared times, or you just figure out the answer. And in either case, you're going to run a polytime. Good. And that brings us just down to the compression. So the question is, I could have given you a break a long time ago. Do you need it, or do you just want to cover? Is everyone following? Does everyone need a minute?
I'm good. You wanna take a break, John? We can take a break. Maybe. We'll take a break.
Maybe like 5 minutes.
Yeah,
breaks
5 minutes.
and
Yeah.
and be done.
Ready. So, where do we leave off? If you give me a K, you guarantee that my weight assignment, that again is written on the catalytic tape. You promise me that for some number K, there is a size K matching which is isolated by this weight assignment. Isolated meaning there is a unique min weight matching of size K in the graph. I can find it using this little gadget and using the determinant. And in fact, I can actually find all of the entries, all of the edges that participate in that matching by toggling things on. This is going to be a very useful property for us. So K is a number we're going to keep track of on the Logspace work tape. And just for starters, what I said should actually probably give you some idea of how we can get around all the recursion that we'd have to deal with if we were building the matching of by augmenting patterns. And that is, all I need to do is certify that K is good enough once, and then I can get that matching whenever I want using the determinant. Right? So this is great. So normally, if I were to do augmented paths or something, I'd have to actually like build this matching on edge by edge using augmented paths. Well, I'd have to store it somewhere. I'd have to do a bunch of recursion. Now I don't have to do any of that. All I have to do is certify that K has an isolated matching of size k in the graph, given this matching or this weight cosine on top. Good. So now I'm going to assume I have it for k, and I'm going to do it. I'm going to certify this for k plus 1. And essentially, there's going to be 3 possible outcomes. The first is that there is a size k plus 1 matching, and there is a mid-weight one, which is isolated. If I can certify that fact, I'm just going to increment k and keep going. If there is no matching of size k plus 1, I will detect this fact, at which point I can simply, I know that the answer is k, and now I can just print that matching to the tape, or I can print the number k. And the third case is going to be that there are matchings of size k plus 1, but there are actually at least 2 min-weight matchings of size k plus 1 with this weight sign. And that's going to be our compression case. Great. And the way we're going to go from k to k plus 1 is augmenting paths. So I've already told you about the residual graph. The residual graph says that given some matching, I'm going to put all of my edges forward except for the edges in the matching. So if this edge is in the matching, it's going to go backwards. If this edge is in the matching, it's going to go backwards. And say those that's it. So everything else goes forward. And as I said before, if I can find an augmenting path of this, which starts and ends on the left hand, starts and ends with an edge going forward, then that defines for me a matching of size k plus 1. And the easiest way to do this is to simply put a new vertex S and T. I'm going to put forward edges in the following way. S is going to go forward to exactly the vertices which are not matched. And similarly for T.
That's good.
Good. For weights, I'm going to put zeros here. On all the forward edges, we're going to maintain their weight. And for all the backwards edges, I'm going to actually do minus them. Okay. Now, even putting aside the weightings, it is clear that if I have an ST path, that is an augmenting path in the graph, right?
Yeah.
It has to go to somewhere which doesn't have any backwards edges in time. So all you do is follow a forward edge, and then whenever it wants, it can hop off and go to T. Except that you can go backwards, so any maximal ST path. Okay. Yeah, okay, I have to be a little bit careful about it. It's not gonna matter the reduction, but yeah, I want to make sure that I don't accidentally like leave some edges on the T. So
Maximal length.
maximum length, but even that's kind of a weird thing to say because why should I have to go backwards and then back forwards? But okay, so you know what? Here's what I'm going to say instead. I'm going to jump to the part where I have weights because this is going to be the interesting part. What is going to be the weight of my ST path? What is that going to correspond to? It's going to correspond to the weight that of my new size k plus 1 matching. If I just add in all the unused edges, the edges in the original matching that don't participate in this path,
Okay.
and now I take the sum of this path, that's going to correspond to this the new weight that I get from k plus 1 because I'm going to every edge that I go down is going to be removed from the weight k plus 1 matching, and every edge forward is going to be added to it. So if I just add all these weights and subtract all these, it's going to count. The crucial part is, oh, right, of course, that's why there's no backwards edge. Any vertex that has a backwards edge is not going to there, right. So any ST path in this graph actually does correspond to an augment. Yeah, there's the trick.
And the difference in weight is the weight of the
Correct. The difference in weight between the two matchings is the weight. Now, as was discussed earlier, this does not necessarily capture all size k plus 1 matchings. Just doing an augmented path on k doesn't by itself capture all weight k plus 1 matchings. But it does capture all min weight size k plus 1 matchings. Okay. It's not even all min weight size k plus 1 matchings. However, if there is a unique min weight k plus 1 size matching. Wait, is that no, all k plus 1 size matchings are. No, that might be right. I think I might be right. I think that's right. Yeah. Then all min weight size k plus 1 matchings are product estimates.
The residual black line.
S2 has in G residual. I have defined this terminology. The residual graph is this one where you have the paths. The S2 thing is the gotcha. And so what's the idea of this? The idea is that any components that are not the augmenting path are going to cause us issues. So let's consider MK what do you call it? Symmetric difference with some new matching n of size k plus 1. Or to call it. Okay, so ignore all edges that aren't in either of them. Keep all edges that are in one but not the other. Throw out all edges that they don't have. Right. So what do you do? Well,
What is MK plus 1 here? Any?
let's do MK. And this is this is some
Mm,
min weight k plus 1 matching.
Okay.
Not assuming it's isolated. All right. So you have some red edges, and you have one more blue. Right?
I think this is not true.
It might not be true. I might have to adjust it.
If you have D min weight size k plus 1 matching, and assuming it was unique, I would agree. Otherwise, I don't see.
Well, let's go through the argument and I'll see where it's wrong with this here.
Right, because suppose that. Oh, maybe.
No, I was right. No. Okay, good.
That is true.
So it looks like you have many different possibilities, right? You can have even length paths, which aren't augmented paths. You can have even length cycles,
I see.
or you might have multiple augmenting paths. we're going to rule out all of these.
None of the even length paths or the cycles increase the weight.
Correct.
If they did, then MK would not be isolated.
So let's deal with all three cases real quick.
Yeah.
So we have even length paths, we have even length cycles, and we have unions of more than one odd length path. And I claim all of these are going to violate some assumption in this claim. The even length ones, you guys basically just nailed it, right? Of course, we're talking about maximum, right? Like if there's more edges here, then I'm going to extend this thing. Again, it has to be essential. Even length cycles are where it's clearest. Consider the weight of this cycle in the plus minus form, right? So the red edges, which are the backwards edges, have negative weights. The blue edges have positive weights. What's the weight of this cycle?
Wait, what?
It's either positive, negative, or zero.
It has to be.
The difference in the sign.
Right. The positive means that there's more weight going forward than coming back, right? Meaning that if I replace these two edges in MK plus 1 with these two edges, I would actually get a lower weight.
No, the other way around. The red is MK.
Yeah, so in MK plus 1, if I replace these blue edges by the red edges,
Okay.
then I would get a matching of lesser weight, right? Oh,
In MK plus 1.
yeah, because his negative weights are smaller than these positive weights in MK plus 1.
Yeah, but
But I assume it's a min-weight match.
you already used this movie.
Yeah. I'm talking about some of min-weight MK plus 1 matching.
Sure.
Min-weight matching is SK plus 1.
Yeah.
So clearly I cannot do this. If MK plus 1 has min-weight, then I cannot just replace these two with these two.
And this is regardless of what matching MK was. Just
Correct. As long as, yeah, exactly. Good. Otherwise, this weight is less than or equal to 0. And now the opposite argument occurs. MK, I could have replaced these two red edges with these two blue edges.
Right, so it has to be 0, but it can't be 0 because MK is unique.
Correct. It could be negative because then it would have a smaller weight. It could be 0 and have the same weight, but then it wouldn't be unique. That takes care of that. Similarly, even, right? Again, assuming this is maximum, like the same with the replacement parts. And what about multiple odd components? Multiple augmenting paths. Well, if there's multiple odd length paths, then there's at least one which is starts and ends in blue, and at least one that starts and ends in red.
Right.
Right? Because in the end, I need the number of blue edges to be 1 greater than the number of red edges. So if there's more than one of these things, and there's no even length stuff, then there's at least one odd length one, which starts and ends in red. And now just consider the union of these two paths. Do the same analysis.
It's an even number.
If it's big, if it's too big, just switch on both of these, get a better says MK plus 1. Otherwise, switch on it and get a better MK. Or the same. So none of this can happen. All you get is exactly one augmenting path.
One odd.
This is kind of the big conceptual. Even though it's like pretty straightforward, and even though parts of this I think have been observed in other places for other reasons, this is what we need, because this tells me that as long as I know the unique min-weight matching of size k, I can recover from it all matchings of size k plus 1. In particular,
All min-weight match.
all min-weight matchings of size k plus 1. In particular, if there is any matching of size k plus 1, then there's a min-weight. Which means if there's no ST path, just for obvious reasons, there is no matching of size k plus 1. And I can report as such. I'm using, again, here implicitly the fact that weighted ST connectivity is in CL. For small weights. I think it's true even for big weights, but that's not even right. Right, I can generate this right. If I can generate MK, which I'm going to do so using the determinant. The determinant will allow me to generate the edges of MK as I need them. And thus, I can put directions on all the edges in the original graph as needed. Plus this Gaussian sum.
Right.
Good. I can see this graph. if there is a size k plus one matching, or if there's no size k plus one matching, SCT won't be connected, I can return if S and T are connected and there is a min weight, a unique min weight matching. Well, again, I can find this out by just testing the weights, one at a time. And I'll just like find out whether or not there, first of all, I'll find out whether there's any pattern.
Sorry. If there's a unique min weight matching for what, K?
If there's a unique min weight matching for K, I can just describe this whole graph. At which point it's easy for me to actually find whether or not there's 0, 1, or more than one min weight matches.
Why? Because you look for cycles?
0 is just there's no ST path.
0, 1 or more min weight matchings of size K plus 1?
Or size K plus 1, yeah, sorry.
Ah,
Min weight matches size K plus.
did I look at the graph?
Yeah.
Now, try to count the number of augmenting paths, I guess.
Yeah, basically, yeah, this is all, you can do this mod some large prime or whatever. You can also, if you find that there is a path, you can remove one edge from it and see if there's still a path. That'll also do it.
See, so then I know. So if I've certified that actually the weight unified, so the weight I have makes the K matching unique, min weight K matching unique. I can now verify if the same set of weights
Yes.
also makes the K plus 1 matching unique. I construct this graph, I will count the number of upward, see if there's more than 2 augmenting paths, and that's the answer.
Correct. That gives me 0, 1 versus more than 1 is exactly the trichotomy I said.
If it's
There's
0,
nothing
I
on K
get
plus
1
1.
K.
Right, if there's nothing of size K plus 1, there's a unique one of min weight one of size K plus 1, or there's not.
See. Oh, that's really cool.
Yeah, this gets you 90% of the way there, right? Like, if there is a unique one, I just increment K, and now I never have to actually do this graph reduction again to find 10K plus 1, the unique one.
No
The
regrets.
determinant will give it to me.
Yes.
Right, so this is kind of the leapfrogging that we're doing. And now I realize I probably should have let off this whole second section of the talk with the proof of the isolation lemma, which extremely suggests why 2 paths, but actually, frankly, we didn't read that proof. We just knew this off the top of our heads because it's like such an easy compression algorithm once you have everything I've described to you.
Okay.
So I promise you that there are 2 min weight matchings of size K plus 1. Meaning there are 2 min weight ST paths in this.
It means that there's a 0 sum.
It means that there's a 0 sum. In particular,
Even like-
you can prove that there is an edge, a forward edge, i.e. a not one from M10, which is in one but not the other. It's just easy. Right?
That is in one of the.
Yeah, so you now have M1 and M2. These are 2 min weight matchings of size K plus 1. There is some forward edge, which is in M1 but not M2.
Sure.
And this is typically called the threshold edge. So.
Oh, so now we need to compress.
Yep. All right. So what do I do now? It's a 0 sum.
So you just need to record what the sum is though. You need the locations.
Yeah.
Right, our weights are much larger.
No, these are log bit, well, the big complexities are like order log. Think
But
of
we
these as
want-
the large one.
We need it to be a large.
Yes, exactly. But log n sharply wouldn't work, and even the numbers I gave you before, little n over capital N tells you that they won't work, right? Capital N is like the number of edges, the universe is the number of edges in the graph. So even for this to be statistically true, I need my capital N, which is when universe size to be at least say like, well, it used to be like 2 times n squared or something like that. So you need like log n, 2 log n plus 1 bits. In our case, just make it 5 log n bits, right? Why play at the margins? Just pick some huge range.
But also, losing what weight this is.
So, oops, I got those the wrong way.
2 log n.
So this edge, let's call this, it goes from edge V to V. The weight of the edge is the weight of N2 minus the weight of M1 without the edge E. And in our graph, that's exactly the weight of the path from S to T minus the weight of S to U minus the weight of U, V to T. And this is in the graph without the edge E. Right? So I take the graph and remove the edge E. If I know there's still an ST path because there's a matching, another min-weight matching. So I just look for the length of the shortest path from S to T without allowing yourself to use the edge E. Then find the min path, length path from S to one point of E. And then the min distance from the other point of the T. Now, by the way, this is exactly Spencer's proof of the isolation lemma, just observed not as a compression algorithm. What's the whole point? The whole point.
Now you can forget that we will.
Now you can forget W. W is being described as quantities which don't involve E. Right? This doesn't involve the weight V. This doesn't involve the weight V, and this doesn't involve the weight. As long as you tell me what E is, and you can write that down using 2 log n bits, just tell me what's E and what's V. Then I can erase W. So
you say log n 5 point.
As long as WE is at least 2 log n plus 1 bits, I've saved myself at least 1 bit. If it's 5 log n bits, I've saved myself 3 log n bits. And so on and so forth. Again, this was his way of doing a probabilistic argument. Where essentially compressor random is a way of making taking probabilistic arguments and making them constructive. Right? It's not just that a random choice works, but I'm actually going to witness the fact that a non-random choice doesn't work. Or I'm going to witness everything that doesn't work.
You compress anything
Exactly.
that doesn't work, you find a way of actually.
Yeah, right.
Yeah.
Great. Now,
Yeah, it's like Rasmorow's switching lemma. It'd be an example. Where he shows an encoding.
exactly. We tried to actually do some funky stuff with the switch lemma. We didn't find how to make everything be interesting. But anywhere where you have a probabilistic argument, it's worth checking if you have a constructive probabilistic argument. If so, you might get a CL algorithm for free. Which there is no higher aspiration as far as I'm concerned. Good. Now, note, what's the important thing here? I can cook up all of these factors as long as I can get access to MK, which I haven't touched, right? MK is not being touched here because I picked edge E to specifically not be in MK. Which means I can still produce using the determinant, which means I can still produce the graph using a Logspace reduction. I now have U and V written down, and I can run all of these weighted tests. This is very specific to being able to do all of these steps in Catalytic Logspace. This works because I can do the determinant, because I can cook up the MK, because I can construct the graph, because I can do weighted ST connectivity. And if any steps of these break down, I don't have the argument. Which is funny, because what I just said at the end here applies no matter what the graph is. If I have 2 min weight size k plus 1 matchings, then there is an edge that's in one and not the other, and that edge weight is determined by this. In some sense, compression is trivial here, and it doesn't even matter what side of the graph. The problem is I have to then get it back. And to get it back, I have to actually figure out what's the weight of M2, i.e. what's the min weight size cable swim matching. And I have to find out what's the weight of this M1 that I've now deleted an edge from. Like what's the weight of the rest of the edges? And that's fine when it's ST connectivity.
Yeah.
Right? The whole point is reducing this question to ST connectivity. If you knew what M2 and M1 were, you could just pull them up off the top of your head, then this would be enough. Right? This still gives you a probabilistic argument, even when we don't have such a nicely structured match and stuff like that. But that's all irrelevant to us, because we have an additional hurdle to overcome, which is compressing in CL. And that was the whole point of all of this, was to reduce to a case where the compression and decompression essentially reduced to very within CL objects.
I mean, but this is it, right? So now once you figure out the edge, you just squeeze, right, that you squeeze everything to the left, right? So you erase it. And then you put the index of the edge, right? So you have calculated, right? Exactly. And there's your E.
Actually, this is gonna be the extra. So I'm gonna look and I'm gonna find the E,
Right,
and after my compression, what is it gonna be?
you just squish everything to the left.
Yeah, I'm gonna write down U, I'm gonna write down V, then I'm gonna have a whole bunch of zeros, which are just for my use. And this is now the way to sign it, minus the weight of E. And what am I gonna do? I'm just gonna take all this extra thing, I'm gonna tack on another 5 log n bits of it, and I'm gonna repeat the process.
But you repeat it from scratch, right? You start from 1.
Yeah. Right now I go back to the very beginning, because now I don't know to decide what the weight of the min weight cable or size K matching is. So append this, you can even actually stick this in as the new weight E.
Wow, that's so nice.
And now you have to start from the very ground floor, but who cares?
I thought you were gonna take like another hour, but it's actually a simple trick. It's just very hard to find.
No, yeah, so this was what I attacked, specifically reducing to some kind of easy thing that is recoverable, where the recovery is done in CL, is what I was starting with. And he just came back in a month later with this.
Okay, I'm now in the non-bipartite. You don't have this augmentation, right?
You don't have, yeah, things aren't so simple. Even LMI, where you sort of have a notion of the augmentation graph, this whole analysis down here is not quite right. Right, like this analysis was a key piece of this, right? If min weight matchings of the same size could be gotten via even cycles or some other like gadgets or whatever, you don't have those. Even this last little step where if I can't pick a threshold edge, which is not in the original matching and whatnot, if I don't have that, then I don't know how to do all of this. I think I wasn't on the LMI paper, so I don't know which of the troubles he ran into, or they ran into, but they had to do some serious hacking around this stuff. Luckily, bipartite matching ended up being straightforward enough that this graph gives it to you. But yeah, no, as you say, this is actually the whole argument. So this is the kind of thing that you can do using compression techniques, which is quite lovely.
Sorry, can you what is happening, like,
Sure.
there with the last part, when you are like, because if I have an understanding, you are trying to, compress that edge that is part of W, right?
Yes.
Okay. And then this is how you're doing, like,
Okay.
like,
So I'm writing down this equation, which I hope you agree with, right? The weight of the edge is just the weight of M2, which doesn't contain the edge, minus the weight of M1 where I don't have the edge, just all the other edges.
yes, yes. And the question I'm missing, what is actually happening, how are you?
So once I've identified the edge, right? My compression scheme is going to just go and see that edge. Okay, I'll write down the names of its nodes, U and V. I can write those down in free rotate for the moment. I'm going to completely erase this. I'm just going to destroy it. Then I'll just, to make things easier, I'll move this to the front of the tape. Right, just rotate everything around. Write down U and V. maybe I have a counter in my free workspace which increments, which keeps track of how many times I've compressed or something.
Yes.
There we go. Right, so I just pull this space out, stick it on the front. This had 5 log n bits, something like that. This has log n bits, this is log n bits.
Okay, yes.
Everything I have is zeros, exactly. And now all I'm saying is to repeat the argument, I'm missing a weight. One of the edges doesn't have a weight. So I'm just gonna like chop off a little bit.
But you didn't need to do it that way, right? You could have just taken the next block as your new W instead of being so efficient with your.
Yeah, of course, I could actually just have like n squared different weight functions.
Yeah.
And I'm just going to run through each of them, and if one of them is not compressible, it's because it gets the right answer. If all of them are compressible, I just get everything in one shot. Yeah, I'm just trying to squeeze water out of stone on this, like,
Yeah.
you can do, actually, the nice thing about that one is very parallel. Right, you can just, like, in some sense, you could run all of them simultaneously, you have some sort of parallel CL model. But the point is, like, I'm allowed polynomial catalytic space, it's just like everything works, right? I'm allowing myself a whole bunch of polynomial here to compute determinants or weighted dimensions or whatever. If the extra more interesting problem is asking, can you do this with much less catalytic space? Or alternatively, can you compress much more bit, many more bits than one log n at a time?
So you could hook, for example, like log n squared, or log n cube or something.
You could, so for example, BPL can be computed in CL, as I mentioned earlier. It can in fact be computed with free space log n and catalytic space only log squared n. A much more efficient derandomization, kind of with
So aren't there the randomizations of the switching lemma? Like PRGs that would fool the switching lemma?
it. You have to say the switching limit in some context, right?
No, I don't mean the switching lemma.
Isolation
I mean
lemma.
Isolation lemma.
Yeah, well, again, in some context. So there's these quasi polynomial size ones. There's like a log squared and bit seed length or something like that.
There you go.
So now you need to compress when it fits. So you know that there's some redundant weight that comes out of it, but how does this actually compress the seed?
Right, I see.
So in the BPL case, this is exactly what happened, right? So this is Ted Pine's paper. We know that if we compute randomized log space using a log squared n length seed, which is essentially log n many hash functions of log n bits. What he showed is that if this fails, it turns out you can index the hash function that caused you to fail into the set of all hash functions that caused you to fail. This is like a
But we're so
Yeah.
so you're saying that you have a de-randomization of isolation lemma, where you can now sample your family of waves using, let's say, log n squared or log n cubed,
Yeah.
whatever bits, right? So somewhere in that argument, so now you see what I'm saying? So somewhere in that argument, you have to prove that works. Right, so that somehow.
yes, so you do right.
So you need
So
to do that argument
constructively, exactly. Yeah, and constructively inside CL. I'm not saying it's out of the question. I'm just saying, yes, that is the thing you have to prove to get it to work. And for the record, I think there's intuition for why that should be like a major breakthrough in. I think that's, well, no, because they have the quasi-NC algorithm, so. I don't know, I suspect this will be hard, but this is obviously the thing that one should do. Right? This is a step that one could look at. Anywhere where you have a randomized algorithm, again, anywhere you have a randomized algorithm and everything besides the randomness is like easy to compute. If you can then tell me also like this kind of determinant for this constructive witnessing of when it's not random, there's a good chance everything towards over C. A good chance. But matching is one of the, like, this doesn't work for RNC in general, right? Or even RNC1. I don't know what the witness is that the randomness is not good randomness. I don't know how to witness that fact. But for matching, this argument does that.
Sure.
Right. If you can do it for, if you can do it for these other randomized arguments like the PRG and whatnot, then you're good to go. Of course, you also have to be able to like, compute the output of the PRG in CL. Just a bunch of things to check.
Excellent talk. Are we any?
I honestly, I think this is pretty much it, unless I'll take you. Yeah, unless there's anything you want to ask about specifically, any extensions, etc. But I mean, this is like, and again, everything that reduces to match bipartite and maximum matching reduces to this. The reductions are all very, very easy. So CL will do just as well for those things.
Good. Now, his passion enthusiasm.
You don't have to tell the camera about it.